So when you think about the whole artificial intelligence boom, I could probably guess exactly what pops into your head. You're picturing these massive server farms, right?
Right.
And
Right.
packed with these incredibly powerful GPUs humming away, crunching billions of parameters for the latest AI models. I
Yeah.
mean, we just hear endlessly about the chips.
Right. It's always the chips.
Yeah. But there is this massive, entirely invisible problem in the industry right now, and it actually has nothing to do with the lack of computing power.
No, not at all.
The real threat to the AI revolution is, well, it's a physical traffic jam. These multi-million-dollar chips are suffocating simply because they just can't talk to each other fast enough.
Yeah, it's really the ultimate bottleneck. I mean, we are engineering these cognitive supercars, right?
Yeah.
But we're basically forcing them to drive on unpaved dirt roads.
Wow, that's a great way to put it.
The raw compute capacity of modern AI hardware has just completely outpaced the physical infrastructure that actually connects it all together inside the data center.
And so that is the core mission for our deep dive today. We're going to explore what Wall Street and the tech industry are calling the optical supercycle.
The supercycle, yeah.
Right, how the entire ecosystem is just desperately swapping out traditional copper wires for microscopic lasers just to save the AI data center from, choking on its own data.
Exactly.
And to do this, we have a really dense stack of intel we're pulling from today for you. We're looking at technical transceiver specifications from FBLINK, the latest product announcements, and silicon developments from Marvell. We've got market supply chain analysis from TrendForce and Stock Alpha, and some financial reviews covering Sivers Semiconductors.
Yeah, and what's fascinating here is that we are looking at a fundamental architectural shift. I mean, this isn't just, an upgrade to a slightly faster cable.
Right.
We're examining a complete physical transformation in how human knowledge, data, and these massive AI workloads are processed at a truly foundational level.
Okay, let's unpack this. Because to understand why we are suddenly having to shoot lasers around data centers, we have to look at the physical limits of our current hardware.
Right, the baseline.
Exactly.
Right.
The sources point to the death of copper. And, I mean, we've used copper electrical links for decades. But AI requires, like, a 10 times increase in bandwidth efficiency.
Mm-hmm.
So why exactly is copper hitting a physical wall at these new speeds? Like, why can't we just, use thicker cables or push more power through them?
Well, it really comes down to the physics of high-frequency electrical signals. When you try to push data at, say, 800 gigabits per second or higher over a copper wire, you run into some severe signal integrity issues.
Okay.
There's this thing called the skin effect.
The skin effect.
Yeah. So at high frequencies, alternating current tends to distribute itself only near the very surface of the conductor.
Oh, I see.
So the electrical resistance just spikes. You get massive signal degradation or attenuation just over a few meters of cable. So to get a readable signal from point A to point B, you have to push an immense amount of electrical power through that wire.
And I'm guessing that creates heat.
Exactly. At AI scale, that power draw becomes impossible. The cables literally get too hot to even manage.
Okay, so the industry's immediate solution is the 1.6T optical transceiver. And looking at the FBLINK specifications we have, I mean, the numbers are just wild.
Oh, they're staggering.
Right. It transmits data at 1.6 terabits per second. And it achieves this by using 8 200 gigabit per second channels that operate simultaneously.
Right.
But it also relies on something called PAM4 modulation. The spec sheet says it, quote, encodes 2 bits per symbol. But, I mean, what is the actual mechanism there? How does that work in practice?
Yeah, so think about traditional digital transmission as just binary, right? Just ones and zeros.
It's like a light switch.
Exactly. It's basically a light switch that is either completely on or completely off. That's called NRZ modulation. But PM4, which stands for Pulse Amplitude Modulation 4 level, it totally changes the game.
How so?
Instead of just on or off, it uses 4 distinct voltage or optical amplitude levels. So because you have 4 states instead of 2, you can transmit 2 bits of information in the exact same time window it used to take to transmit just 1.
Wow, okay.
Yeah, you're effectively doubling your data density without having to actually double the physical clock speed of the laser pulsing.
Okay, so if traditional copper is like a sloppy bucket brigade where electrons are bumping into each other, facing all this resistance, and water keeps spilling out.
Sure, yeah.
Moving to these 1.6T fiber optics with PM4 is kind of more like building a frictionless water slide. You just encode the data into light, drop it in, and it slides to its destination with almost zero resistance.
That's actually a really accurate way to visualize it. You're basically removing the friction of electrical resistance from the data's entire journey across the data center floor.
But You know, I need to push back on the logistics of actually deploying this stuff.
Sure.
If a data center rips out all its old gear and plugs in these massively powerful 1.6 terabit per second modules everywhere, doesn't that just completely blow up their existing power budgets? Like generating and modulating lasers at that speed, it sounds like it would require astronomical amounts of electricity.
You'd think so, right? But the irony is that the exact opposite is actually true.
Wait, really?
Yeah. The magic of this 1.6T transition is the efficiency gain per bit. So if we look at the FBLINK data, a single 1.6T transceiver consumes roughly, I'd say, 20 to 25 watts of power.
Okay.
But if you wanted to achieve that exact same 1.6 terabits of bandwidth using the older generation of hardware, you would need two 800G modules. And those two older modules combined, they draw about 36 to 40 watts.
Oh, wow. So by upgrading to the faster tech, you are actually cutting your power usage.
Precisely. By doubling the speed per lane from 100G to 200G and utilizing much more advanced silicon, data centers can cut their total system power for that specific network connection by like 30 to 40%.
That's a huge drop.
It is. And when you're operating a hyperscale facility with literally hundreds of thousands of individual connections, that marginal efficiency translates into massive operational savings. You essentially reclaim megawatts of power that can now be fed directly into the GPUs doing the actual math.
Right. Feeding the beasts.
Mm-hmm.
But you can't just like tape a laser to a fiber optic cable and expect it to automatically modulate 4 different amplitude levels at 1.6 terabits per second.
No, absolutely not.
It takes incredibly sophisticated logic to orchestrate that signal. And I think that brings us to the actual silicon chips, the brains powering the light.
Yeah, you need highly advanced digital signal processors, or DSPs, to act as the traffic controllers here.
Right.
Because as that PAM4 optical signal travels, it inevitably gets distorted. The DSP's job is to sit right at the receiving end, take that messy, distorted analog waveform, sort of clean it up, and perfectly reconstruct the digital ones and zeros before feeding it into the main switch.
And the sources highlight Marvell as a massive player in this specific space. They just rolled out their new 3-nanometer 1.6T DSP portfolio. So they have the Era-T, which handles transmit retimed optics, and the Era-X, which is focused on broader link reliability.
Yeah.
And the key detail that stuck out to me here is the 3-nanometer architecture. Because they shrank the transistors down to that microscopic node size, the electrons basically have less distance to travel inside the chip, right?
Oh.
Which means it generates less heat.
Exactly.
The Marvell announcement actually claims this cuts power consumption by another 20% compared to older designs.
Yeah, it's a critical engineering leap. And the innovation, it isn't just limited to the signal processors either. We're seeing major validation on the laser side as well. Yeah. If you look at the financial reviews of Sivers Semiconductors, they show this really fascinating development. Jabil, which is a massive, like $30 billion contract manufacturing company.
Huge company.
Right. They have officially partnered with Sivers to build these 1.6T pluggable transceivers at scale.
Now, the Sivers review noted that Jabil is specifically leveraging Sivers' indium phosphide laser arrays. Why is that specific material so important? I mean, why can't we just use regular silicon for the lasers, since we use it for, literally everything else in computing?
That's a great question. Silicon is phenomenal for computing and switching logic, but it is physically terrible at actually emitting light.
Really?
Yeah, it has what physicists call an indirect band gap. If you pump energy into pure silicon, it mostly just releases that energy as heat, not light.
Oh, that's definitely not what we want.
No, not at all. But indium phosphide is this exotic material from the VIAV group on the periodic table, and it has a direct band gap. So when you apply an electrical current to it, it efficiently emits these pure, high-quality photons.
Yeah.
And the Jabil partnership is significant because Jabil, they do not invest in niche experimental tech. Their involvement proves that integrating indium phosphide lasers into these 1.6T modules is fully ready for high-volume global deployment.
So what does this all mean for the physical data center then? Because honestly, I am spotting a massive contradiction in our sources.
Oh, what's that?
Well, we just spent this entire section outlining how incredibly power efficient these new 3-nanometer DSPs and 1.6T modules are.
Yeah.
Right? Like they use less power per bit than the last generation.
Right, they do.
But then if you look at the FBLINK deployment specs, they clearly state that thermal management is still their absolute #1 headache.
Yes.
Yeah, some of these fully retimed modules can still draw up to 28 watts each. If a data center populates just a single network switch with 64 of those pluggable ports, that is nearly 1,800 watts of localized heat. just from the optic.
Just the optics, yeah.
And that doesn't even include the heat from the switch chip itself. So how can it be highly efficient and simultaneously overheating?
So if we connect this to the bigger picture, you really have to separate power per bit from power density.
Okay, unpack that.
The power required to send a single megabyte is way, way down. But because we are cramming so much more bandwidth into the exact same physical space on the server rack, the absolute heat generated in that tiny area is just unprecedented. Power really has to be budgeted by the physical architecture of the module, not just by the line rate.
Okay, so it's like taking a highly efficient LED bulb, which barely uses any power, but then cramming 1,000 of them into a single shoebox. Like, the efficiency doesn't matter anymore. The shoebox is going to catch fire because the density is just way too high.
That perfectly illustrates the thermal wall these data centers are hitting right now. I mean, at 1,800 watts across a single faceplate, standard air cooling is just completely maxed out.
You just can't blow enough air?
No, you cannot blow air fast enough to carry that kind of heat away. So it forces physical design changes on the transceivers themselves. Like, they're having to integrate closed-finned heat sinks directly into the metal casings just to channel airflow perfectly. Wow.
And ultimately, it's forcing the entire industry to rapidly transition to liquid cooling just to keep the optical components from physically melting.
Which basically means we are already outgrowing the 1.6T pluggables before they have even fully taken over.
Kind of, yeah.
The sheer heat and power demands are forcing the industry to mass produce an even more radical architectural solution, right? Co-packaged optics or CPO.
Exactly. CPO changes the fundamental layout of the entire network. But to understand it, you first have to look at how a traditional pluggable transceiver is physically connected inside the box.
Right. So with the pluggables we just talked about, you have this massive switch chip sitting right in the middle of a circuit board. And when data needs to leave the switch, it has to travel as an electrical signal across several inches of copper traces on that circuit board just to reach the front panel where the optical transceiver is actually plugged in.
Right.
And only then is it converted into light.
And at 1.6 terabits per second, pushing a delicate electrical signal across 4 or 5 inches of copper trace is just devastating to the signal integrity. It's just too far.
Yes. It requires massive amounts of electrical power just to push the signal those last few inches to the laser. So CPO eliminates that journey entirely.
Wow.
Instead of plugging the optics into the front of the box, co-packaged optics takes the laser and the photonics and bonds them directly onto the exact same substrate as the switch chip itself.
Oh, wow. Here's where it gets really interesting. It's like, instead of driving a truck to a train station miles away just to ship your package across the country, the freight train is now pulling directly into your living room.
Ha, exactly.
Right. There's no middleman, and there's no long drive. The optical conversion happens instantly right next to the logic chip. And this isn't science fiction. This is actively happening right now.
Oh, very much so.
A TrendForce report highlighted that NVIDIA is already putting CPO into mass production inside their new Spectrum X switches. And this is being built to support their upcoming Vera Rubin AI platform, which supposedly boasts 3 times the performance of their current chips. And Broadcom is doing the exact same thing with their 51.2T Bailey CPO switch. According to the data, CCO reduces power consumption by up to 70% compared to traditional pluggables.
It is a staggering reduction in power consumption because, I mean, you completely eliminate the need to drive electrical signals across the circuit board. The photons basically just take over immediately.
Wait, okay, I'm losing the thread here. Let me just stop you for a second.
Sure.
If co-packaged optics cuts power by 70%, and NVIDIA and Broadcom are already mass producing it today, doesn't that just completely kill off the 1.6T pluggable market we literally just spent the last section talking about?
Well,
I mean, why are companies like Jabil and Sivers pouring millions into pluggable transceivers if CPO makes them totally obsolete? And furthermore, if CPO bakes these fragile lasers directly onto a $50,000 switch chip, what happens if a single microscopic laser burns out? Like, do I have to throw away the entire switch?
okay, so this raises a very important question. And you've hit on the exact reason pluggables are not dead. Pluggables will remain the dominant force in the data center through at least 2028.
Okay, why?
Because while co-packaged optics is definitely the ultimate destination for the industry, it is incredibly difficult to manufacture at high yields. Like you just said, if you bond fragile photonics directly to a massive silicon switch and one single laser fails testing, the entire package is basically compromised.
Right.
You'd lose 50 grand. Exactly. Pluggables offer modularity. If a laser burns out on a front panel pluggable, a technician just unplugs it, throws it away, and slides a brand new one in. It takes 10 seconds, and your $50,000 switch keeps running without missing a beat.
Okay, so the hyperscalers, the Googles, the Metas, the Microsofts, they need massive bandwidth today. They can't just sit around and wait for CPO manufacturing yields to perfect themselves over the next decade.
Exactly.
So pluggables are the bridge technology.
Yes, CPO is scaling, but pluggables are the absolute vital bridge for the next 5 to 7 years to ensure that these AI models can keep growing right now.
And this desperate, simultaneous need for both advanced pluggables and next-generation CPO that has triggered what looks like a massive supply chain war.
Oh, a huge one.
The Stock Alpha report quantifies this optical supercycle, and the numbers are just massive. The optical interconnect market is projected to surge from $16 billion to $41 billion by 2030.
Wow.
Shipments of 800G and higher transceivers are jumping from 24 million units to 63 million units in just a single year.
I mean, we have never seen a ramp up like this in the optical sector. Never. And I think the clearest indicator of this kind of industry panic was NVIDIA actually stepping outside its normal boundaries to write a $4 billion strategic investment check split evenly between two optical manufacturing giants, Lumentum and Coherent.
$4 billion.
Yeah, that is a massive capital commitment solely to lock down their optical supply chain.
But, just pouring money onto a problem doesn't magically bend the laws of physical manufacturing.
If only it did.
Right. TrendForce outlined 3 major bottlenecks that really threaten to derail this entire supercycle. First, optical engine manufacturing yields. I guess it's notoriously difficult to perfectly align microscopic lasers and modulators.
Very difficult.
Second, silicon photonics capacity. Fabricating these wafers requires extreme precision, and the global industry simply does not have enough specialized fabs built yet.
Nope.
And third, advanced packaging shortages.
Yeah, the advanced packaging bottleneck is easily the most critical constraint in the entire global supply chain right now.
Okay, wait. Let me make sure I am fully understanding the reality of this. So the solution to our AI GPU data bottleneck is to build these co-packaged optic switches, right?
Right.
But those CPO switches require TSMC's COPE advanced packaging technology just to combine the silicon and the optics.
Yes.
But isn't that the exact same advanced packaging capacity required to assemble the actual AI GPUs themselves?
You nailed it.
Are they literally fighting for the exact same microscopic real estate on TSMC's fabrication lines? That just sounds like a zero-sum game.
It absolutely is. That is exactly the bottleneck. The optical interconnects required to scale the network and the compute engines required to actually do the math, they are cannibalizing each other's manufacturing capacity right at the packaging layer.
Wow.
Because there are only so many advanced packaging machines in the world, and this zero-sum game is forcing the industry to completely rewrite its playbook.
Wow, so
Vertical integration is becoming mandatory. NVIDIA is aggressively deepening its strategic ties with TSMC to secure that packaging volume, while hyperscalers like Google are actively trying to develop optical components entirely in-house.
just to bypass the lines entirely.
Exactly, to bypass the external supply chain bottlenecks entirely.
And this brutal bottleneck is also why alternative innovators are suddenly so valuable.
Very true.
The Stock Alpha report highlighted a company called Poet Technologies, and they are basically bypassing the traditional low-yield manufacturing methods using an innovation called an optical interposer.
Right.
So from what I understand, instead of trying to individually align and glue these tiny indium phosphide lasers onto the silicon one by one, POET is bonding the 3V materials directly with the silicon at the wafer level.
Yes.
So it sounds like they're basically printing the entire optical engine as a single integrated piece.
It's really a highly elegant engineering solution to what has historically been a brute force problem. Traditional laser coupling, aligning the light source with the silicon waveguide, it is painstaking.
And slow.
Very slow, and it's prone to microscopic errors that just ruin the yield. So by integrating the light source at the wafer scale using an interposer, POET bypasses one of the most painful, time-consuming steps in silicon photonics manufacturing. They are fundamentally changing how the hardware is assembled to sidestep these existing bottlenecks.
And the supercycle isn't just enriching the hardware manufacturers either.
Oh,
The sources point to a company called VIVI Solutions.
Yeah.
And they don't make the lasers, they don't make the switches, they make the testing ecosystem.
which is crucial.
Right, because at 1.6 terabits per second, single speck of dust on a fiber optic connector or like a microbend in the cable, it can cause massive signal back reflection and just completely ruin the link.
Oh, easily.
So VIEV provides this highly complex lab-to-field validation equipment required to ensure these hyperscale networks actually function before a company turns them on. I mean,
yeah.
they are the ultimate picks and shovels play in this gold rush.
They really are. The testing ecosystem is so often overlooked, but it is vital because you cannot just plug in a 1.6T network and assume it works like some old Ethernet cable in your office.
Right.
The tolerances are microscopic. Without companies providing rigorous automated validation gear, these multi-billion-dollar data centers would basically just be unmanageable black boxes of signal errors.
Wow. All right, let's bring this deep dive back down to earth and talk about what this means for you, the listener. Like, why does this invisible, highly technical physical layer matter to your daily life? We've journeyed all the way from the physical melting point of traditional copper wires to the photonics-driven 1.6T modules utilizing PM4 just to cut power consumption.
Yeah.
And ultimately to the radical future of co-packaged optics, where the laser and the logic chip become one.
Right. And what this really boils down to is that the AI revolution has fundamentally shifted. I mean, for the past decade, we were entirely compute-bound.
Just building bigger brains.
Exactly. The race was just to build a faster brain. Well, we have the brains now. Today, the revolution is interconnect-bound. So every time you ask a complex question to an AI tool, every seamless response, every generated image, it is all physically made possible by these microscopic laser breakthroughs.
It's all light.
Yeah, if the optical supercycle fails to deliver, the entire AI boom stalls out completely.
It all comes down to clearing that physical traffic jam inside the data center. But before we wrap up today, I want to leave you with a final lingering thought to explore on your own.
Oh, I like these.
Right now, light is entirely replacing copper inside these massive data centers simply because of bandwidth limits and heat generation, right?
Right.
But how long will it be until those exact same physical limits force this technology to shrink even further? Imagine a future, and maybe not that far off, where optical interconnects are no longer just for the hyperscalers. Imagine them required directly inside your personal laptop, just to connect your CPU to your memory.
It's coming.
Or inside your smartphone. Or eventually imagine bypassing electronic interfaces entirely, using light to directly link our biological brains to computational interfaces. I mean, if copper is dying in the data center today, its days are definitely numbered everywhere else.
I couldn't agree more. The migration from electrons to photons is just the natural evolution of physics and computing. As our need for speed and efficiency scales, light will eventually be the only viable medium left.
So the next time you marvel at how fast an AI generates a response, don't just think about the chips doing the math. Think about the invisible grid of lasers working frantically in the background just to keep it alive.